In this video, we're going to look at how to solve systems of inequalities by graphing and determine the coordinates of the vertices of a region formed by the graph of a system of inequalities. How can you determine whether your blood pressure is in a normal range? During one heartbeat, blood pressure reaches a maximum pressure, systolic, and a minimum pressure, diastolic, which are measured in millimeters of mercury. The blood pressure is expressed as the maximum pressure over the minimum pressure, for example, 120/80. Normal blood pressure for people under 40 ranges from 100 to 140 for maximum and from 60 to 90 for the minimum. This information can be represented by the system of inequalities. So anywhere in that shaded region, so between the 100 and 140 on the maximum and between 60 and 90 on the minimum, there's an infinite number of points in there. Well, if you count decimals, I suppose. It would be finite if we only restricted ourselves to whole numbers of combinations that you could have of your minimum and maximum for your blood pressure. To solve a system of inequalities, we need to find the ordered pairs that satisfy all of the inequalities in the system. One way to solve a system of inequalities is to graph the inequalities on the same coordinate plane, like we did for blood pressure. The solution set is represented by the intersection on the graph. To solve this system by graphing, we're going to graph both lines, and they gave them both to us in slope-intercept form, and look at the intersection. To graph the first line, it has a y-intercept of -3 and a slope of +2, so it's going up 2 over 1, and the boundary is included, so we need a solid line. To graph the second line, it has a y-intercept of +2 and a slope of -1, so it's going down 1 over 1. This time the boundary is not included, so we need a dashed line. The first inequality said greater than, so we shaded above the solid line, and the second said less than, so we shaded below the dashed line. So they're using the awesome property of colors that yellow and blue make green, so their final shaded region is the green one. So it is above the solid line and below the dashed line. Now, this system of inequalities has a line and an absolute value graph. I'm going to start with the absolute value, even though it's second. But we know absolute value, we want to do case 1. So x plus 1 is less than 3. And case 2, x plus 1 is greater than -3. If we subtract 1 from both sides, we have x is less than 2. This is a less than, so it should be and. If we subtract 1 from both sides there, x is greater than -4. Okay, my boundary is at x equals -4. The boundary is not included, so we counted 4 units to the left, vertical line, and it is dashed. And x is less than 2, 2 units to the right, vertical line, which is also dashed because the boundary is not included. My linear equation had a y-intercept at 1 and a slope of -1. Remember, if there's not a number in front of your x, you can always put -1. So my boundary is y equals -1x plus 1, and this time the boundary is included because it's less than or equal to. So I put a point at 1, and my slope is going down 1 over 1, down 1 over 1, down 1 over 1, and the boundary is included, so a solid line. It's shaded below the orthogonal line, line that is not horizontal or vertical, and between the two dashed lines, because we want x to be less than 2 and x to be greater than -4. Now, most of our graphs are going to look like the ones in example 1, where we have a nice region in between our lines that's shaded. But then there's always an exception. If we graph these two, they have the same slopes. The lines should be parallel. They have different y-intercepts. So it's not the same line, it's two different lines, parallel. First line has a y-intercept at 1, the slope is going down 3 over 4, and the boundary is included because it was greater than or equal to. The second line has a y-intercept of -2, and it is also going down 3 over 4. Okay, if they had reversed these, we could shade the region in between, but they said no, 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 no. They want us to shade above the line that has a y-intercept of 1 and below the line that has a y-intercept of -2. So, are there any points that satisfy both equations? The answer is no. In mathematics, that is the abbreviation for the null set or empty set, which can also be written with two sets of braces with nothing between it, but we seem to prefer the circle with a line through it. Medical professionals recommend that patients have a cholesterol level below 200 milligrams per deciliter of blood and a triglyceride level below 150 milligrams per deciliter. Write and graph a system of inequalities that represents the range of cholesterol levels and triglyceride levels for patients. Yeah, you cannot have a negative level of something in your blood. So these are both going to be first quadrant graphs. 0 is our boundary. For cholesterol, the maximum we want to have is 200. They said less than 200, so I didn't make it less than or equal to. And triglycerides, same thing. We cannot be negative. And the biggest, they want it to be below 150. Okay, so there's our system of inequalities. It's going to be very nice to graph because we're just going to have a vertical and horizontal line at 150 and 200. Now on a problem like this, our photocopied graph paper is going to fail us because the scale is all messed up. I would honestly just sketch a first quadrant graph on my paper if I were you. And they labeled nicely by 50s, that's easy enough. They labeled by 50s, nice enough. And does it matter which one's the independent, dependent variable? In this case, absolutely not. So if you had switched triglyceride and cholesterol, it would not matter. So just as long as you have them labeled, it's all good. So they have T, a dash line at 150 because you don't want to equal it. And for C, a dash line at 200 because you don't want to equal it, and shade less than both of them. Find the coordinates of the vertices of the figure formed by 2x minus y is greater than or equal to -1, x plus y is less than or equal to 4, and x plus 4y is greater than or equal to 4. Okay, we need to solve for y so we can graph, and then on the graph we'll see where they cross, and those will be our vertices. So subtract 2x from both sides. And honestly, at this point, all we're doing is finding vertices, so I really don't even need the inequality. I'm copying it down because it's there, but it doesn't really matter. So y is less than or equal to 1 plus 2x. Okay, so we have a y-intercept at 1, a slope of 2. Oh, that second one's lovely. Subtract x from both sides, and we've got that. So y is less than or equal to, I'm going to put it in the order we're used to seeing it, -x plus 4, so it looks like y equals mx plus b. I guess I could have done that to the other one too and written it as y is less than or equal to 2x plus 1. Okay, and then our last one, we have x plus 4y is greater than or equal to 4, subtract x. So 4y is greater than or equal to -x plus 4, divide by 4. Y is greater than or equal to, that'd be -1/4 x. 4 divided by 4 is 1. The first line has a y-intercept of 1 and a slope of 2, so it's going up 2 over 1. The second line had a y-intercept of 4 and a slope of -1, so it's going down 1 over 1. And the third line had a y-intercept of 1 also, but its slope was -1/4, so it's going down 1 over 4. You will want to use nice graph paper and straight edges because when you do, it will be clear to see where your vertices fall. So I've got 0, 1. 0, 1 is true for the equations that were originally 2x minus 1 and x plus 4y equals 4. You could substitute back into the equations, make sure it works. 1, 3 is true for these two equations, and 4, 0 is true for those two equations. And this is going to lead directly into lesson 3-4, where we will want to use those vertices to find maximums and minimums in an organized way called linear programming. A solution of a system of inequalities is found by graphing the inequalities and determine the intersection of the graphs.